How AI-powered analytics and optimization software is helping the steel industry reduce emissions through improved energy efficiency. By Issam Mazoud, Technical Sales at DecisionBrain, Jose Favia, Director, Global Industry 4.0 Leader at IBM, and Dr. K.N. Srikanth, DecisionBrain, North America. This presentation is adapted from a presentation delivered by DecisionBrain in collaboration with IBM at the 2022 Hannover Messe conference in Germany. This year's conference showcased how industrial transformation is progressing while tackling the dual challenges of climate protection and energy security. DecisionBrain helps organizations improve efficiency with flexible planning, scheduling, and logistics optimization software. Today's talk comes out of some joint work between DecisionBrain and IBM in the steel industry. We will highlight one particular project focused on maximizing the productive usage of flammable byproduct gases. So let me start with the problem statement. Steel production is one of the largest man-made sources of greenhouse gas emissions. 7 to 9% of all fossil fuel-based CO2 emissions are derived not from the metals industry in general, but specifically just from the steel industry. For every 1 ton of steel that's produced, 1.85 tons of carbon dioxide are produced. And a big part of why is because it takes a lot of heat to transform iron ore into steel, and that energy comes from burning fossil fuels, often coal. Here's a 2019 breakdown. The biggest emitters are actually on the bottom, and you see steel right there in the lower right, comprising a total of about 7 to 9% when you exclude the non-fossil fuel-based sources like livestock. The last slide was focused on greenhouse gas emissions, but the steel industry generates both greenhouse as well as the more toxic byproduct gas emissions, which, similar to carbon monoxide, are flammable. When these gases must be emitted, they're typically burned or flared in order to reduce their toxicity, though the burning does transform them into greenhouse gases. The project we're detailing today is focused on maximizing the productive usage of these byproduct gases so that instead of flaring them early, they can be used downstream, thereby reducing overall energy waste and the emissions that result. The solution was developed using a combination of advanced forecasting and optimization technology. Now let's dive a bit more into the details. Let me start with a couple of diagrams on the steelmaking process. The important thing to note here is that steps 2 and 3, which are the iron making and steel making steps, these are where the flammable byproduct gases are produced, often in excess, which is why they are burned or flared. Now, the following steps, like the rolling mill where steel slabs are converted into plates or coils, there are very complex scheduling decisions to be made in each of these downstream processes as well. And another great opportunity for the application of optimization technology. However, the focus of this presentation is on the emissions reduction opportunity, which is greatest in the 2 circled steps. Drilling into these steps a little more, most of the world's steel is still produced through what is called the basic oxygen furnace steelmaking process. Raw materials, including iron ore, coal, and limestone, go through a variety of processing steps in equipment like blast furnaces, coke ovens, and others. Each of these stages produce different byproduct gases referred to as BFG, COG, and LDG. These names are less important than the fact that a lot of these gases are burned off early in the production process instead of being sent further downstream where they are actually useful. And this is the hard problem that we're tackling in this use case: how to reduce the amount of flaring at these earlier stages so that we can be more efficient overall. Here's one more way to show the process. Here we're looking specifically at how these gases flow through the pipelines and the other equipment that's involved. Note that there are actually 5 different gases we're working with, shown on the bottom left. This network has different nodes and pipelines. The nodes can be supply nodes, like in the upper left. You have 3 LDG gas supply nodes, where various and somewhat hard to predict amounts of LDG come in, which we're going to come back to. You also have demand nodes like 12 and 14 with energy demand that can be partially or fully supplied by LDG. And then you also have storage nodes. where gas can be stored. And another type of downstream consumer is in red, a transformer, which is like a gas mixer. So the first part of the problem is forecasting both the supply of LDG gas that will be coming in, as well as the downstream demand by the gas consuming steps. Now, there are many complex and sometimes interrelated factors that drive both supply and demand, which we're not going to get into here. But what I will say is that these two forecasting problems are very much like most forecasting problems we see out there. We use machine learning technology to train a forecasting model. And we do this by feeding in lots and lots of data about the potentially causal drivers of, say, LDG gas supply, as well as the corresponding readings of actual supply over specific time periods. And we do this continually over a time period and then let the AI engines learn and build the model. Then once we have that model, we can apply it in the future to make better predictions. In virtually every industry, the ability to accurately predict is critical to good decision making. So now imagine we've solved the first part of the problem. We have really good demand and supply forecasts. Now we get to the part about what do we do about it? Or what are the levers we can play with in order to minimize waste? Okay, so they're not actually levers here. They're more like gas flow valves, but you get the point. I've overlaid here with stars the various control points in the process, meaning the points where decisions must be made, like what volume of gas we want to allow to flow. For those familiar with steel manufacturing, you will probably recognize all of these control points. But for the rest of us, what's important to note is that in any process or flow in which you have many decision points, which can interact with each other, and when you have constantly changing input data, like actual gas supply and demand readings, as well as forecasted future values, that means you have the opportunity to constantly make sets of interrelated decisions for each plan period. This way, when I sum up the result of all the decisions over the time period, I get the best overall result. But here's where we find ourselves with a really hard problem with way too many possible permutations to choose from. Not only can't you solve this in your head, but you can't even solve this problem very well with if-then logic rules. Rather than being a rules-based problem, what we have here is really a mathematical optimization problem. In mathematical optimization, we model problems in terms of supply, demand, constraints, and goals. So we already talked about the gas supply and demand points. The constraints are things like tank capacity limits, pressure limits, and many other such rules that either can't or shouldn't be violated. And then lastly, you have a set of goals. Some of the goals for this problem are listed here. We want to minimize waste from flaring. We want to optimize gas holder volume because there's a performance penalty for holding too much or not enough gas. We want to maximize energy sent to the powerhouse. Remember our first goal about reducing energy waste and emissions? This is how we model that. And finally, we want to optimize the number of active burners or powerhouse boilers because that's a switching cost. So the way the optimization solvers work under the covers to quickly solve this combinatorially complex problem is outside the scope of this presentation, but I will say that optimization solvers are a very mature technology that have been used for decades to solve the world's hardest planning, scheduling, and logistics problems in nearly every industry. And the proof is really in the results. So now let's talk about the impact of all the work we did implementing advanced forecasting and optimization software technology. This particular client that we have been discussing is not fully deployed yet, but preliminary results have already shown a more than doubling of the amount of LDG that was able to be sent to the powerhouse rather than being burned early. Or put another way, they improved their energy efficiency by cutting the amount of LDG gas that was flared down to less than a third of the original amount. This is thanks to improved forecasting, together with letting an optimization-based system direct the flow of gas along the various pipelines. IBM and DecisionBrain have collaborated on many projects. Here are a few other examples within the steel industry. One is a large steel producer in China who's also focused on reducing energy costs and greenhouse gas emissions through better forecasting and optimization. The second is an Indian steel manufacturer who is optimizing the scheduling of oxygen generation to minimize waste through venting and realized a 15% waste reduction. And the third is a Latin American steelmaker who is looking to reduce and save on natural gas costs. And like the case study we just talked about, also wanted to reduce gas emissions. But instead of focusing on LDG gas, they were focused on two other flammable byproduct gases. The thing to note here is that these savings are not unique to steelmaking. Across all types of continuous and discrete manufacturing industries, it is not uncommon to see 10 to 20% improvement and often more on the KPIs that manufacturers care about, like throughput and on-time orders and waste and emissions reductions. Going beyond manufacturing, IBM and DecisionBrain have delivered optimization solutions to many industries and across all types of planning, scheduling, logistics, and workforce optimization use cases. So if you are in any resource-intensive industry, whether those resources are materials, goods, or people, and you think there are inefficiencies in your planning, scheduling, manufacturing, logistics, or workforce management processes, consider solving them with advanced forecasting and mathematical optimization technology from IBM and DecisionBrain. Please feel free to reach out to us if you have any questions.